Hello and welcome to Lecture 31 of my class from Data to Decisions. I'm Chris Mack, your instructor for this class, and this is the second part of a multiple-part series of lectures on the topic of total regression. In the first part, we talked about the effective variance approximation. The idea of total regression is that there is potentially some variation in variables regressing against, the predictor variables or regressors, which will influence the way the regression works. If the variance in X is large enough that it has some impact on the Y variance, but not so large that it dominates that, we can apply the effective variance approximation. It basically says, I'm going to let our best estimate of each X variable be the value of the X variable we have, and then define an effective variance in Y equal to the variance in Y from all other sources plus the variance in Y that comes from X. So if I have some variation in X given a certain slope, that will translate into a certain variation in Y. If I add that variance on top of the source of all the other variance in Y, I get an effective variance. Then we use a weighted least squares fit for these uncertainties and do the regression using weighted least squares. I'd like to talk now about a special case that occasionally happens. It's doesn't happen very often, but under certain circumstances, we might find that every single xi has the same variance and every single yi has the same variance, and they're equal. That is, these two terms, yi and sigma xi, are identical. When that's the case, the effective variance simplifies. First of all, it's no longer a function of I, it's the same value for every data point. And it's equal to the variance in Y times 1 plus the slope squared. If the slope happens to be constant as a function of xi, that is, we have a straight line model, single slope, then we have a constant effective variance. It's proportional to 1 plus true value of the slope quantity squared. And so I can use that as my weighting, and 1 over that actually as my weighting, and the chi-square becomes this. Well, if the weighting is a constant, then it doesn't really matter, right? If a constant weight produces the same best regression result as a non-constant weight. But this weight is a function of beta 1. And beta 1 is also in our equation, our model. So yi hat has a beta 1 in it too, as well. So we have beta 1 here and beta 1 here. Now when I try to minimize this sum of squares, I'll find that weighting has an impact. So if I take this chi-square and take the derivative with respect to beta 0 and set that equal to 0, I'll find that the results are exactly like we saw before. But when I take the derivative of chi-square with respect to beta 1, I'll get a different answer. And this is what we're going to do in this case. This special case when sigma x equals sigma y. And we call this special case orthogonal regression or orthogonal distance regression. You'll see why when I show you a graphical meaning of this regression. For right now, though, we can think of it like a maximum likelihood estimator. We take the derivative with respect to the parameters, set them equal to 0 to maximize the likelihood, minimize the value of chi-square. When we do that, right, there's just some algebra you have to do and you get an answer. It turns out the answer for the intercept is the same as we've seen all along, but the answer for the slope is a little bit different. Here's the equation. It has the variance in x, the variance in y, the covariance in x and y, all the same terms that we calculate anyways in doing our regression. And so it's simply a different formula for the slope. Of course, we also have to find out the standard error of our estimates, but I'm going to talk about that actually in the next lecture. going to talk about this time, but stay tuned. An estimate without a standard error of that estimate is almost useless. So we have to have standard errors of these estimates as well. The geometrical interpretation of an orthogonal regression is as follows. Under ordinary least squares, what I'm trying to minimize is the vertical distance of each data point compared to the best fit line. So I'm going to take the sum of the squares of the vertical distances and try to minimize that sum of squares. That's what ordinary least squares does. What orthogonal least squares does is it takes a normal to the best fit line and says what is the position of this best fit line, which minimizes the sum of the squares of the normal distances to that line. It only works if we can assume that the variance Sx and Sy are both constant and they're both equal to each other. When does that happen? When do you ever get this weird coincidence that the variance in all of your x values that you measure is exactly equal to the variance of the y values? Well, it is rare. It doesn't happen too often. But it does happen when you're trying to measure the same thing with two tools that are nominally identical. This is a problem called tool matching, or maybe it's process matching. I've got one method of making a measurement, and I've got a second method of making a measurement. I take the same sample and I measure it twice, method A and with method B. I want to compare. So we sometimes call this comparing methods. So this is a regression approach that's used for comparing method A to method B to see how they relate to each other. In that case, if the two tools for making the measurement are nominally identical, we can expect them to have nominally the same level of uncertainty in the measurements. Because I'm measuring the exact same sample two times, sample is the sample. The sample is not changing. Well, we hope the sample doesn't change between measurements. And therefore, we expect a straight line between these two unless there's some nonlinearity in the behavior of these tools relative to each other. What we're generally looking for here in a tool matching is something like a calibration curve. We're looking for a slope and an offset that would allow us to calibrate one tool compared to another. And this happens a lot in the world of making measurements. Sometimes it happens quite frequently. This is very, very commonly used in chemical analysis and biological analysis, testing for antibodies or for other chemicals that might be present. And you have multiple labs that can do these testings, and you'd like all the labs to give the same answer. So we need to be able to match what one lab uses as an answer compared to another lab, or one method of measuring compared to another. And so these kinds of orthogonal regressions are frequently used in those applications. There's another interesting case that comes up where I've got some data, some x values and some y values, and I want to do a regression to compare them, but I ask myself the question, which should be x and which should be y? We generally think of x as the fixed value, the thing that I change and I know what it is, and y is the response, the thing that I'm measuring to see how x affects the response. But there's some situations where it's not obvious that y should be the response and x should be the thing that causes that response. Most common example of that is what we might call natural variation. That is, there's something that is causing, or looking variable, causing both x and y to change, and I want to know what the relationship is. But x is not changing y is not changing x. There's just some natural variation, some lurking variable that's changing them both. Similar to the calibration curve and tool matching application, if I am purposely varying sample, I can measure it with two different tools, but the variation that occurs has nothing to do with the change in the sample, but it is due to variations in the two measurements. So sometimes the tool matching calibration curve examples can be thought of in the same way, but not always. So if we have this natural variation, how do I decide which x to use, which variable to use as the x, the predictors, and which variable to use as y, the response? Sometimes we want a regression method that is symmetric, that doesn't make me choose. Here's an example. This is from a study that was done a long time ago, not that long ago, I guess, but kind of a famous study where they measured a whole bunch of people looking for metrics that were easily measured in a doctor's office that would give some indication of the amount of body fat on a person. So they measured what's the circumference of the hip, the circumference of the chest, neck, the forearm, the biceps, the wrist, all these different measures of the body in the hopes that some combination of measures might be a useful way of predicting the amount of body fat, which has lots of health consequences. So here's two of those measures. So the thing that is varying is the people. Right? Every data point is a single individual person, and those people vary. They have all kinds of different sizes and shapes. But basically, if somebody is small, they have both a small hip and a small chest. If somebody is big, they have both a big hip and a big chest. And so these two measures are varying together. But I'm not changing one to see how it affects the other. There's no natural way to say one should be y and one should be the x. And if I do a least squares regression, I will get different answers depending on whether I pick one to be x and one to be y. So if I pick hip circumference as y and chest circumference as x, I get this blue line, fit line. However, if I picked x, the chest circumference as my response, and the hip circumference as my predictor variable, I'll get this dotted line as my best fit. Very different response, depending on which one I pick as being y. Which should I use? Well, one approach to answering this question is the geometric mean regression. It basically says, I'll do both. Regress y given x and regress x given y. I'll get two different best fit lines. I'll get two different slopes. Of course, once I have one slope, I can invert it to get the equations in the same forms, but they'll have different values for the slopes. So I'll take geometric mean those two slopes and say that is my best estimate, when I don't really care which is the predictor and which is the response. So we can do this actually analytically. We don't have to actually do both fits. We find that the estimate of the estimator for the intercept is identical, but the estimator for the slope is the standard deviation of y divided by the standard deviation of x. Whereas if I did an ordinary least squares, assuming all the variances in y, that is the x values are fixed, then I get a different value of the slope. I get covariance of x and y divided by the variance of x as my estimator for the slope. So we get a significantly different value, and sure enough, its value is somewhere in between the two extremes of assuming all the error is in x versus assuming all the error is in y. I get the in-between result. Now in this case, I also show the orthogonal regression result at the same time. It's about the same as the geometrical mean regression. That just is because in this particular case, variance of x, variance of y are about the same. So the assumptions of an orthogonal regression also hold true approximately here. Of course, that's not always the case. In fact, frequently not the case. There is a third way that we can think about uncertainty in x and how it affects our regression. And this is using an estimation method that we haven't really talked about in this class, and I'm really not going to talk about much in this class, other than to mention that it exists. It's called the method of moments. That is, you have an estimator for the first moment, the average value. You have an estimator for the second moment, which is the average value of the response squared, etc. You have multiple moments that you can create estimators for, and then you combine them in order to get estimates for the parameters of your model. These method of moments estimators tend to be pretty good when you have a lot of data, and maybe not so good when you don't have much data. Higher moments have a huge amount of uncertainty in them unless you have a lot of data. So we tend to only use the method of moments estimators when we have a large number of data, and this one is often referred to as good only if you have more than 50 data points or 100 data points. So in this model, suppose that we say that the x values equal the true value plus some error, and the error is normally distributed about a mean of 0, and that we have a good estimate for the variance in those x values. Then the method of moments estimator for the slope can be related to the OLS estimator for the slope by dividing by 1 minus this ratio of variances. Well, this tells us a couple of things. First, it tells us something about the direction of the bias that comes in an OLS estimator when we ignore variation in x. Bias is always in the same direction. The OLS estimator will always be smaller in magnitude compared to the true value whenever we have variation in x. The other thing is we can get a reasonable understanding of the magnitude, or what kind of effect in size that we can expect. And it's the ratio of the uncertainty in x to the total range in x we've used in our experiment. If the uncertainty in x is a large fraction of the total range that we've used in our experiment, right, so S sub delta is the uncertainty in any given x measurement, and S sub x is the standard deviation of all my measurements, all the x values. In other words, it's something like the range of the x values that we've used. When that ratio is appreciable, then I get a big difference between the OLS slope and our method of moment slope. But when that ratio is small, then there's not much difference. And this is another way of saying if the uncertainty in the measurement in x is kind of small, then we don't have to worry about it too much. And here we're going to measure uncertainty in x in any given measurement as compared to the range of the x values we're using in our experiment. A very similar approach happens when we think about the OLS estimator in the limit of an infinite number of data points. This is a more general topic called consistency. The consistency is the property of an estimator as the number of data points goes to infinity. We say an estimator is consistent if it is bias-free as the sample size goes to infinity. Now, sometimes you get estimators that are biased. That happens. The second question, once you've realized your estimator is biased, is how is that bias affected by the sample size? And if the bias goes to 0 as the sample size goes to infinity, we say that the estimator is consistent. Unbiased estimators are the best, generally, all other things being equal. But even if you have a biased estimator, at least you want it to be consistent. Well, in the presence of uncertainty in the x variable, the OLS, ordinary least squares estimator, of the slope is not consistent. The bias doesn't go to 0 as the number of data points goes to infinity, as long as there's uncertainty in x. In fact, you can show that as n goes to infinity, our estimator for the slope goes to the true value divided by 1 plus ratio of variances. Again, it's like we saw in the last slide. The method of moments estimator gives just about the same answer as this OLS estimator bias calculation or consistency calculation does as n goes to infinity. It's the ratio of the uncertainty in a given x value measurement compared to the standard deviation of all the x values, that is, the range of x that we're using. So either by thinking about this consistency argument, thinking about the method of moments estimator from the previous slide, we can get an understanding of the magnitude of the issue as long as you have a large number of data points. If you have a small number of data points, things change. But if you have a large number of data points, you can at least find out whether this is an issue you need to worry about. As long as this ratio is small enough so that the variance in a single measurement is small compared to the variance in all the measurements, the whole range of measurements that you've done, you can decide whether it's a big enough effect for you to worry about. All right, what have we learned in Lecture 31? First, what is orthogonal regression and when is it useful? What is geometric mean regression and when is it useful? And finally, what do the method of moments and the consistency measure the asymptotic behavior of the OLS as n goes to infinity? What do those two things teach us about the effect of x uncertainty on a slope or a straight line model? Well, we still have more total regression topics to discuss, different methods of doing total regression, and we'll talk about them next time. Till then.